Hear me?
Yes.
Okay. So let me share the screen. Can you see the screen? Okay, so
Yes.
okay. Okay, so thank you very much for introduction. Okay, I'm Reiji Suzuki from Nagoya University in Japan. Today, I would like to introduce the design of a virtual agent that facilitates the spatial and online communication by use of social particle swarm model. This work is mainly done by Meito Tsuruta, but he has already graduated. So today I would like to introduce this work. Okay, the impact of the COVID-19 has changed our daily life dramatically. And as like this kind of situation, our face-to-face communication has been limited, and instead opportunities for online communication increased. In particular, spatial and online communication services called proximity chat has attracted attention. This is an example of this type of the services, spatial chat and office and the gather.town. So as you might know, in this kind of system, each participant is represented as an avatar or icon in a virtual 2D space, and he or she can move it around the space. And he or she can listen to the neighbor's voices, and the volume becomes louder as they get closer to him or her. But there are some issues because this is expected due to the limitation of information channels or cues, such as a lack of non-verbal cues discussed in the previous presentation, such as eye contact or nodding or touching or some ambient noises and so on. This might make participants to lose chances to communicate with other people because the overall structure of communication tend to become deadlocked. For example, in some cases, each group tends to be isolated from one another once some groups are formed. And also, it is not easy for participants to figure out the timing to leave the group when the group size is small because of the lack of the queue of the opportunity due to the limitation of information channels. So the mechanism that can compensate for such a low relational mobility situation would be necessary. And also there is an increasing attention in designing a hybrid society composed of the humans and virtual agents to be cooperative or pro-social. For example, the performance of group behaviors can be improved when a bot is put into a group of humans performing cooperative or collective tasks. So the purpose of this work is to consider novel application of A-Life techniques to design co-creative, meaning the mutually cooperative and creative social dynamics in a spatial and online service, such as a proximity chat. For this purpose, we design and investigate a virtual agent called a facilitator agent as an initial step of this work. This agent gives the human participants opportunities to communicate with many others cooperatively. For this purpose, we use the social particle swarm model to simulate the group dynamics in this type of communication service. So let me explain the model. This model is designed for analyzing the continuously changing social dynamics. As you see, the human individuals are represented as particles like this. And we assume the two-dimensional toroidal space. In the original model, we assume that this space approximates the structure of all possible communication channels, including both physical and online social networks. But in this work, we assume that this space represents a virtual space in a spatial online communication services, such as room and venues or something. In this model, each particle has a strategy for the prisoner's dilemma game, so cooperate or defect. In this work, we assume that the cooperative particle is contributing to the discussions among neighbors individuals by providing useful or interesting information for them. On the other hand, defecting particle represents that they are not interested in the topic or only exploiting the knowledge provided by others or simply boring. So I mean that the information exchange between individuals has some kind of a cooperative aspect. And the model time step of each time step composed of two phases in this model. One is a strategy selection. In this phase, each particle simultaneously decides whether to select cooperation or defection in a tit-for-tat fashion. For example, each agent has a cooperation threshold C. This represents its tendency to select cooperation strategy, in this case, 0.5. And then the agent selects cooperation as a strategy for the next time step if the proportion of the cooperators among neighbors within the interaction radius R is equal or larger than C, and otherwise selects defection. So in this case, the proportion of cooperators 0.75. So this agent chooses cooperation. Also, this selected strategy is flipped with a small probability accidentally. In the next phase is a movement. Each particle receives attracting or repulsive forces from game theoretical relationship with neighbors. The direction of this force is determined by the sign of the payoff values. So if the payoff value is positive, like this agent receives the attraction force from the neighbors. On the other hand, the payoff value is negative, this agent receives a repulsion force from the neighbors. And the magnitude of this force is determined by the payoff value, but it is scaled inversely with the distance between them. This represents that the shorter the distance is, the stronger their relationship is. Then resultant force from all neighbors determines its moving direction with a constant speed. And the particle without neighbors moves in random direction. So basically, the particle moves getting closer to the agent who can get positive payoff and get away from the agent who gives the negative payoff. So when we conduct the experiment, we can see the three classes of the global behavior like this. The class 1 is a case like this. And more than half of all particles select defection and move around repelling each other. In the class 2, most of particles select cooperation and get together in clusters like this and attracting each other. That's quite stable. But we focus on the class 3, like this. This is a cyclic process of formation and collapse of cooperative clusters repeatedly. We think that this situation reflects dynamic aspects of the real-time communication, group formation, and collapse, and desirable in that they can exchange, they can have chances to communicate with many others cooperatively. Actually, we observe the similar kind of formation of cooperative cluster and collapse in a web-based experiment with human participants. So our purpose is to make this kind of situation to like this by incorporating the facilitator agent into this situation. So let me explain the facilitator agent. This is designed to according to the fixed game and the movement strategies. As for the game strategy, it's quite simple. Either always cooperate or defect at this stage. And as for the movement strategy, we have assumed three strategies. Random walk. In this case, the agent moves in a random direction. And the Levy flight case, that moves random direction, but the speed follows the Cauchy distribution. So sometimes a long jump happens. In the approaching neighbors case, the agent moves closer to the center of mass of all neighbors with a fixed speed like this. And we also assume the two additional parameters that determine the degree of the influence of the facilitator agent on neighboring particle. One is a difference in its interaction radius RA from those of the other particle R. So larger RA is, the more distant neighbors can be affected by the facilitator agent. And another one is a payoff coefficient beta. each neighbor receives a payoff beta times larger than the corresponding normal payoff from the facilitator agent. So for both parameters, the higher value corresponds to the stronger effects of the facilitator agent on neighbors.
5 minutes left.
Okay. Let me explain so the degree of the novel and the cooperative communication is quantified like this. This is a proportion of the pairs that established the cooperative interaction for equal to or more than n time step among all possible pairs through the experiment. N is the depth of the cooperative relationship required for establishing novel social relationship. That may vary actually according to the context or purpose for communication, but for simplicity, we assume that just a fixed value 5. Anyway, the population with high NC is more co-creative in that they can exchange their ideas with many others cooperatively. So this is an experimental setup. We assume that the default parameters like this, and the basic situation is like this. So some clusters happens like this. And we assume the 2x3 combination of the type of the facilitator agent. This is a result. Each heat map corresponds to the type of the facilitator agent. So random walk, levy flight, approaching neighbors, and also cooperate and defect. And each value represents, this axis shows that the average payoff coefficient, and this axis shows the difference in the interaction radius. And each value is the average NC in each setting represented as a rate of the increase or decrease from the NC in the case without facilitator agent 0.46. So the blue represents a positive value and the red represents a negative value. So the blue corresponds to the case when the facilitator agent has positive effect on the global behavior. So as you see, the facilitator agent has strong effect on the NC. In some cases, that this value increase up to 18%, but it decrease up to the 22% from the original condition. And we see the two types of the facilitator agent could typically increase NC when the degree of the influence was high. One is a defecting agent following the levy flight or random walk. And the other one is a cooperative agent approaching the center of mass of neighbors. So this is an example typical behavior. This is a case of the defecting facilitator agent with levy flight. The pink one is a defecting facilitator agent. This sometimes gets close to the cooperative cluster that triggers explosion of a cluster. In some other case, the defectors repelled by the facilitator agent further caused an explosion. So the direct effect and the indirect effect. So this case shows that wandering and broadcasting not so interesting information or even noise might facilitate the communication. On this case, shows the cooperating facilitator agent approaching neighbors. In this case, this is a cooperator agent. This moves towards a cluster, but they gather others. This makes the size of the clusters increase. That triggers an explosion of a large cluster. In this case, so the gathering participants by broadcasting and attractive information or topics to make others join an existing cluster might increase the NC, the degree of cooperative and novel communication. Okay. So we also conducted some experiment using deep learning to acquire the behavior of the facilitator agent. Because this is a challenge to design an adaptive behavior of individuals in terms of the global benefit in a multi-agent situation automatically. I will skip the detail, but we use the reinforcement signal as the amount of increase in the NC at each time step. This is a very initial stage of study, but we observed some behaviors such as moving straight with a defection strategy to explore the 4 toroidal space. And also we could see that occasionally gathered other particles to create cooperative cluster from the initial time step. Okay, in conclusion, we examined the application of AI-life techniques to design a social dynamics in an online space composed of a hybrid of human participant and a virtual agent using SPS model. We could see that this kind of two types of facilitator agent can facilitate novel and cooperative communications. And there are several directions of the future works. But one interesting direction is to incorporate the facilitator agent into a real online communication system on a 2D virtual space plus spatial audio. Actually, we are developing this kind of virtual space services called social particle chat. And we are trying to incorporate that observed the behavior of the facilitator agent into this kind of space. Okay, okay, that's all. Thank you very much for kind attention.
Thank you very much, Reiji. We have time for take one or two questions. Is there anyone who wants to ask a question? Raise your hand or put in a chat. Okay. I have one question. Like in your simulation, looks like there's I'll say a large number of population, but
yes,
but in our actual meeting, we don't sometimes have that amount of people, like much less number of people. Do you think is there any scale effect? Like if your simulation with less number of people?
Thank you very much for question. Yeah, that's quite important. Yeah, so usual daily meeting that I think that there should be a smaller number of people. So yeah, maybe, yeah, actually, yeah, but even in such a kind of situation, maybe that I think that this kind of online space is somewhat not so dynamic. So the adding the this kind of dynamical aspects into that kind of space can contribute to the more active communication. I guess I expect. And as for that scale, we are trying to simulate the similar model using a large scale model composed of the much many number of individuals. In this case, we could also see some kind of clusters. So maybe the similar type of the behavior might happen even in the large scale situation. But I think we have to consider that how actually that this kind of situation might correspond to in the real online communication system. Thank you very much for the question.
Thank you. Is there any question or otherwise let's move to the next speaker. Thank you, Reiji.